so this example 2 that I'm going to do is related to example 1. So it's saying if the V root mean square of the helium and carbon dioxide both double, what is the new temperature of the gases? So remember they were at 25 Celsius first, right? But if we are told that their root mean square double, what does that mean? What is the new temperature of the gases? B says if the temperature of the gases doubles, what is their new root mean square of the gases, right? So here we're doubling the root mean square, so we have kinetic energy is equal to 1/2 mv root mean squared, right? So if the root mean square is doubling, what's happening to the kinetic energy? So this is more like a ratio problem. If the right, so we can write 2v root mean squared. So all we're going to do is touch the root mean square and double it. And then if you square the double, then you're going to get here 4 times 1/2 mv root mean square, right? So this is the new v root mean square, which is twice the old v root mean square, right? And then you're squaring that. So then you're going to have 4. That means the kinetic energy is going to quadruple, right? But remember, the kinetic energy is 3/2 nRT, right? For 3/2 nRT. That means the new temperature is going to be 4 times the old temperature, right? So we can say 3/2 nRT prime is equal to 4 times 3/2 nRT, right? I'm not changing the number of moles and the gas constant, of course. So that means the new temperature is equal to 4 times the old temperature, right? So what was the old temperature? 25 Celsius. The new temperature will be 100 Celsius, right? Not really, right? You can't quadruple the temperature in the Celsius scale. You have to quadruple it in the Kelvin scale. So we can say the new temperature is 4 times the old temperature, but we have to have it in Kelvin. So the temperature was 298.15 Kelvin, right? So then I'm going to quadruple that. 4 times 298.15, right? And then the new temperature is going to be 1192.6 Kelvin. So the temperature in the Kelvin scale quadruples. Then I can subtract 273.15. And I can say this is the answer in Celsius. So the initial temperature was 25 Celsius. The final temperature is going to be equal to 919.45 Celsius. Okay? So the Celsius temperature goes way up from 25 all the way to 919, but the Kelvin temperature quadruples. Okay? How about the second part, B? In the second part, the temperature actually doubled. What happens to the V root mean squared, right? So the temperature went from, the initial temperature was 298.15. The final temperature is 2 times 298.15. So what's happening to the root mean square velocity? Okay? So the difference is that in the part A, you're doubling the root mean square, and therefore the temperature is quadrupling. In the part B, you're doubling the temperature. What's going to happen to the root mean square? And therefore it's equal to 3R T final is what? 2 times T initial over M. So what am I changing? I'm only changing the final temperature, and I'm doubling it from TF to 2, right? And then I can factor the 2 out. I can say square root of 2, square root of 3R T initial over M, right? So that the new root mean square, V prime root mean square is going to be square root of 2 V root mean square. So if you double the temperature, the root mean square velocity goes up by a factor of root 2. But if you double the root mean square, the temperature goes up by a factor of 4. Okay, so the root mean square has more of an effect on the temperature, but the temperature has less of an effect on the root mean square because there's this square root relationship, right? So the old V root mean square for the carbon dioxide was 411. So the new root mean square, 411 times root 2, that's going to be 581.2 meters per second. And then for the helium, okay, so you can see that the velocities both went up by a factor of root 2. Okay, so now you can see the difference between doubling the temperature versus doubling the root mean square velocity. Okay, thank you very much.